Good evening everyone. Welcome to the second video on the video series of IB to IIT Transition and its preparation required for it. So we were discussing about one of the important problems. See, this was regarding an orbital velocity. So wherein you have an Earth and you have a satellite, and this satellite was seen to be moving around it. And the first part of the problem, I asked you to find out what is the orbital velocity and the time period, which were very easy to find out. Typical IBDP or a CBSE problem, anybody can do it. Then the second thing that we looked at is that, okay, the level 2 was about to discuss about, okay, when you have another satellite or maybe a different mass is being added to it, or maybe there is a force, extra force in addition to the force that is acting on the satellite. If there's an additional force was being added, then what will happen to the velocity of the satellite? And that's what we asked, and we were not supposed to calculate anything, and we came to know that if the orbit's radius was same, then definitely the velocity will increase, right? That's what we have seen. And then we came to know about how do you calculate that velocity. We just equated mv square by r is equal to the total driving force, wherein that extra velocity, that extra force was also been added, and we found out what is the velocity required for it. And based on it, we found out what is the time period, which is total distance by total velocity. Okay, we got this one also. Third level was something like I introduced the actual problem, and in the actual problem, instead of giving you the force, I had given you the potential, and the potential was not a regular gravitational potential, but there was a repulsive potential. And the question was, how do you address this problem? So I showed you about how from the potential energy you can arrive at something like the velocity, the force, and from force, how do you get the value of the velocity? Okay, so thus we felt that IIT problem is not so tough. Only thing is we need to understand the problem clearly, what is given, what is not given, how do you proceed further, that's what is required. Now, in today's video series, we will look at one more problem, which is related to something like magnetic field. Okay, so you have a current carrying conductor kept in an external magnetic field. You know what will happen? There will be a force acting on it. But instead of acting on a force, there is a torque being observed. When will a torque be observed? Because when one of the end is being pivoted, for example, if this is the magnetic field over here and you pass an electric current like this, and this is being pivoted, which means what? It's been fixed. Then what will happen? Though there will be a force acting on it given by your FBI rule, but still what can happen is there would be something like a rotation of it, because it cannot move, so it has to rotate like this, right? It can rotate like this, or maybe it can rotate like this. This is what we are going to understand. A very simple problem, but let us see how we can complicate it. Okay, because IIT is all about going into depth and then understanding how to solve it. Okay, let me share my screen. Just a moment. Okay. So a straight current carrying wire of length L, L is equal to how much? 0.5 meters, carries a current of 2 amperes and uniform magnetic field of 0.1 Tesla. I is given, B is given, L is given, the wire is perpendicular to the magnetic field. Calculate the magnetic force acting on the wire. How do you do? Very, very simple question. So what you do is, you can easily find out what is the value of F. It has been given by IBL sine theta, right? You can find out here. So therefore, your value of F would be equal to, what is your I? 2 ampere multiplied by magnetic field. What is magnetic field? 0.1 multiplied by L. L is nothing but 0.5. 0.5, and the wire is perpendicular. Sine theta is sine 90, which should be 2 into 0.5 is 1, 1 into 0.1 is 0.1 Newton. 0.1 Newton. Okay. If the wire has a mass of 0.02 kg, what acceleration would it experience if it were free to move? So what you need to do is, the force is given over here, mass is given over here. You need to find out what is the acceleration. How do you find the acceleration? Acceleration is equal to force by mass, right? F equal to ma by Newton's second law. Apply that and you get this as 0.1 divided by 0.02, which would be 1 by 0.2, which is nothing but equal to 1 by 2 is 0.5. This is 5 meter per second square. Okay, very simple problem, nothing else. Okay, so we have done this. Okay, let me skip this slide. Now let me go to level 2 problem. First problem is very easy. Anybody can do it, whether it is a CBSE student or maybe you are an IB student or ICSE. Okay, anybody can do it. Now next level, let us impose or let us put some complexity into it. What is the complexity here? Now all this is same, it experiences a magnetic force that try to rotate it. Now what's happening is a circular wire carrying current is placed in a uniform magnetic field. Initially the loop hangs vertically due to gravity. So what does it mean? Okay, so loop is hanging like this. It's hanging like this. Okay, very similar to what I have here. I'll show you something. It is very similar to it. So you can see there is a bangle over here, and this bangle is seen to be hanging with the help of a wire, right? So when a current is passed through this bangle, through this wire, or maybe through the bangle, then what can happen? See, there is no current in the wire, there is only a current passing through the bangle. What will happen? Now this will start moving like this over here, right? Why should it move? Now where is the magnetic field? That's the very next question we need to ask, right? Okay, a circular loop carrying current is placed in uniform magnetic field. The magnetic field could be directed upwards. It's upwards like this. Let us say, for example, it is being directed upward like this. It's been directed upward like this. Then it experiences magnetic forces that try to rotate it. It tries to rotate it. So what will happen? It will now go upward like this. So why should it go? What forces are acting? Now let us answer the question over here. Why does the loop tend to rotate when current flows? When current is flowing, how is the current flowing? Current is flowing in this direction. It is flowing in this direction. I'll draw it over here. Current is flowing in this direction over here. Now why should it rotate? Very simple thing. Now what we do is, let us not consider the bank, let us consider this over here. Now how do you arrive at the magnetic force? You are going to use your FBI rule. Okay. So to find out what is the direction of the torque or what is the direction of the force acting on it. Okay, so towards it, what is the magnetic field? Magnetic field is like this over here, left hand rule. Magnetic field is upward like this. Where is the current? Current, the problem in current is that current is everywhere. See, it is flowing like this, it is flowing like this, it is flowing like this, it is flowing like this. Everywhere it's flowing. Okay, you can ask me why anti-clockwise. You can always consider clockwise also. Okay, you can consider any current for time being. Okay, this I felt it's easy for me. I'm doing this for you. Okay, I'm doing anti-clockwise. If you're looking from that side, you're looking at it as a clockwise one. Okay, now if I consider my fingers like this, what does it tell you? Magnetic field is like this, current is like this, which means I am looking at this current. Let me call this point A here. Now what is the force? Force is outwards, which means what? The ring that I had over here, I'll just show you. The ring that I had over here, the bangle that I had over here is now been pulled upward like this, right? It's been pulled upward like this. So it's been pulled upward like this. I hope you are able to see. Been pulled upward like this over here. Okay, so this is now being pulled upwards. Now where is it getting pulled? Is it getting pulled at this point? It is getting pulled at the center of mass. It is getting pulled here, pulled like this over here, pulled like this over here. Okay, now what about the, let me take only 4 points. Of course, you can take every point over here, but let me take only 4 points. Let me consider this point over here. Let me call this point as A. I will take this point B over here and ask the same question. What happens to this point over here? Is it B also been pulled like this? Let us do this exercise once again. So B is like this, that is the magnetic field is like this, and where is the current? Current is going upwards. See, the direction of my current is wrong here, right? So it is like this over here. This direction is applicable only for point A. It is not applicable to point B. Okay, so therefore now how should the direction be? It will be like this. If it is like this, that is a magnetic field and the current, both are parallel vectors. If there are parallel vectors, then there is no force acting at this point, right? There is only a force acting at this point. The force acting at point B is equal to 0 over here, and only at point B. Okay, at the rest of the points we have. Okay, now if that is the case, let me investigate what happens over here at point C. Now at point C, what's happening over here? Current is going in the opposite direction. So B is like this over here. If the current was moving like this, then the force is like this. If the current is moving like this, oh my god, twisting this is very difficult. What I do is I consider this finger to be here. Magnetic field is not changing, so this should change. Now this should be directed inwards to you. Okay, which means this should be directed inward like this over here. Okay, so there is a force acting definitely here, is directed inwards over here. There is a force acting here, directed outward over here, outward over here. Okay, I wrote it like this. Let me write it like this over here. Okay, there are two forces. So as a result of it, it should rotate. But unfortunately, this force is acting at the point of contact. Okay, what will happen? Will it be able to move the point of contact? No, because it's been held firmly, so it will not be able to oscillate the wire. It has been held firmly. So therefore, the bangle itself, the wire itself, or the loop itself now try to rotate because of this force only. It tries to move like this over here, right? It tries to move upward like this over here. So thus, The loop tends to rotate when the current is being flowing. Why does it rotate? Because now what is the answer here? You can now answer saying that it tends to rotate because a current carrying conductor is placed in an external magnetic field, right? A current carrying conductor is kept in an external magnetic field, experiences a force, right? So this is what I need to write. So I'll write here, I'll write a current carrying conductor experiences a force in an external magnetic field. So as a result of it, it starts rotating. Let me keep it here. Okay, next. Which parts of the loop experience the strongest magnetic force? Which parts? Now that also we have addressed. As you see, which parts will experience the strongest magnetic force? So let's make cursor here. It's here. Okay. So this part will this part experience the strongest magnetic force? Definitely it has been lifted upon. What about this? It will not experience the strongest, which means he's asking you which one has a very high value. So only point A, the lowermost point, you can say lowest point on the loop will experience a magnetic force. Okay, then now let us, okay, I don't have space over here. Let me go for this itself. Now, two questions have been answered over here. Let me take up a different color. Red may not be visible here. Let me take up a white over here. So this question is answered. This question is answered. If the magnetic field is vertical and the current flows clockwise, in which direction will the loop rotate? So how do you answer this? Loop tend to rotate. So you have the loop like this over here, and this is the wire which is being connected. There is a current which I said it's going like this. Now suppose if I change this direction, if I change it like this, then what can happen? Okay, now first let me write down the first scenario. The first scenario is like this. Current was going like this, and the force or the torque was seen to be like this. The force was acting like this, and hence, okay, so this is the perpendicular. So after this, what happened? So it became like this. This is the perpendicular. This is the diameter, and this made an angle theta like this. And this was the way how it has been lifted upwards. It has been lifted upwards, then lifted upward like this over here, right? So it experienced a torque. Why did it experience a torque? Because it's a fixed distance, and so there was a rotation being seen. That's why we call it a torque. Okay. Now, if the current, see, if the current was going in the anti-clockwise, this is how it has been lifted upwards. If the current is moving in a clockwise direction, then what could have happened? Then this could have gone like this over here. Okay. So this is a perpendicular. This is what it is. And then this could have been the theta, and it could have been lifted inwards, right? It could have been lifted inwards. So initially, let us say, for example, I have this. Okay. Initially, it has been lifted like this. Then it could have been lifted like that, right? So that's what could have happened. Okay. So this also we have understood. What happens when the gravitational torque balances the magnetic torque? Very naya hai. Okay. So new thing. So far we have been only talking about a torque due to the magnetic field. Now suddenly what I am imposing? I am talking about gravitational torque. So why do we get a torque? First of all, we get a torque because there should be a force. There should be a, let us, for example, if I have an object like this, okay, and now this is on a table. I apply a force. Where do I apply a force? I apply a force here. I apply a force here. Now I ask, what will happen to the object? Will it rotate or will it move? Usually in kinematics, if you have studied well, then definitely you will say, then the force will make it to move like this. But actually what can happen is, if there is a friction here, this is the center of mass, okay, and if you start applying the forces over here, if the friction is larger, there's a possibility that this can topple like this. This can topple like this, right? It can topple like this, and thus you take up one point. For example, if I take up this point over here, initially this point was here. Now this point is here. Now what has happened? It has moved in a circular path like this, and after some time what will happen? This will fall like this. So therefore it moves in a curve. Okay, if I keep something, for example, if I take my mobile over here, okay, and then I keep it like this, and I apply a force here, I apply a force over here, then what can happen? When I apply a force, it will start rotating like this over here. right? Provided I keep it fixed over here. Okay, so therefore the same thing is happening over here. Whenever you want to, you apply a force and one end of it is fixed, then there is a rotation being seen. So what will happen here? Gravitation is also a force. Now where is the gravitational force acting? Gravitational force, for example, in this case, okay, gravitational force is acting like this over here initially. When this has been applied, gravitational force is acting like this. Always remember, force is always acting at the center of mass. It's not acting at any other point. It is acting like this over here. Let me call this as mg. Okay, now we have a fair idea. Okay, we have been speaking about the torque. Is this question is very much what you call, can be attempted very much only by an HL student. An SL student, you need to know about the torque and the rest of, and if you know all this, then definitely you can also do it. Okay, since you are not learning the chapter on rigid body mechanics, you will not be able to do this clearly. Okay, so all this basic concepts an HL student has already learnt. Okay, a CBSE student, whether it is HL, SL, you don't have anything like this, you will always learn all this. Okay, much more tougher problems you have learnt, but still you feel, array, JEE Advance, I can't do it. No, it's not like this. CBSE students can easily do it. That's why you say CBSE can do it, but IB students, you need to practice a little bit. Okay, now comes the actual demand. The actual demand is JEE Advanced problem, which tells you a thin, stiff, insulated metal wire. Okay, I need to change my pen once again. I changed my wire here. Okay, I'll make it as black here. Okay, insulated wire is bent into a circular loop. Okay, so we have a circular loop and there are two forks and there's a wire which has been kept over here. Magnetic field is kept here. See, the problem is very similar to what you have learned earlier. Okay, the loop has a mass m, radius r, and it's a uniform magnetic field B0. It hangs vertically downwards because of acceleration due to gravity and two conducting supports at P and Q. So indirectly it says there is a torque due to magnetic field. Okay, so then because of acceleration due to gravity and two conducting supports at P and Q, when a current I is passed through the loop turns above the line PQ by an angle theta. So what is extra here? Right, there's nothing extra over here. You learned whatever you have to learn in the previous one only, but you are going to now do the mathematics behind it, right? So that's what you're going to do. See, actually in all the problems that we do in our IB or CBSE, okay, so you just learn the context there. But when you learn the context, ask the question, how do I arrive at a math behind it? That means you are going to solve your IIT problem easier. Okay, right now. So therefore it is been like this. Now what is the current? Let us say, for example, it is moving in this direction. It's going in this direction, anti-clockwise, I will say. Okay, if it is moving like this, what's the direction of the loop? Okay, so it is getting lifted up like this, outward, because outward I can always visualize. Inward, I cannot put my finger inside the loop and pull it like this, right? So therefore, if it is going like this, it has been pulled like this over here. Now what will be the new diagram? New diagram would be, it would be like this, and this is your diameter, and this will be your angle theta over here. This will be the angle theta. Now where is the mass acting? Mass of this ring is acting like this over here. So mg is acting like this over here, and then this has been pulled like this. So this is the force, the magnetic force which is acting over here. Why magnetic force is drawn like this? Because magnetic force will always be perpendicular to the area. Okay, so what is the area? Area is nothing but this area, right? Pi r square is here. Okay, that's what we have. So it's definitely perpendicular. Okay, fine, we have done everything. Now where is the math? Now the math, what does it tell you? See, we will consider one point. Okay, we will consider one point where there is a stability being seen, because he is considering some angle over here. At this angle theta, why should this be theta? That's the next question we need to ask. Okay, if this is theta, that means at that point there are two torques which are getting balanced, right? If one of the torque was higher, that will never be theta. The theta would have been increasing like this. But what do we say? That there is one value of theta. Okay, and then at that point we assume that this FB, the torque due to the magnetic force, is balanced by the gravitational force torque. Okay, torque due to the gravitational force. So we need to say that torque due to the magnetic force is equal to torque due to the gravitational force. Okay, now let us find out what are these values. Now towards it, what IB students have not learnt here is this part. You do not know the expression for the torque due to the magnetic force. There is something which is very small that you need to learn. Okay, definitely you need to know this, and only then you can solve it. Otherwise you cannot solve it. But this you already know. Now what is torque? I'll write it down here. Torque is equal to force multiplied by distance. This should be equal to force vector, distance vector, displacement vector into sine of the angle between F and D. Okay, that's what it is. So towards it, now you see the mg, let us do it first for the mg over here. So where is mg? Mg is acting like this. Mg is acting like this. And what is the displacement vector? Now let me show you once again. I'll take up this bangle. Okay, now as a result of it, if it has been lifted upward like this, if it's been lifted upward like this, now you see, I'll write it here. This was the actual bangle, the ring. If it has been lifted upwards, it's been lifted upward like this, then what will happen? So this was the initial radius, this is the final diameter, this was the initial diameter. This has been lifted upwards over here by an angle theta over here. That means it's been displaced. So this part has been displaced by a distance d over here, the perpendicular distance, right? So what I will do is, I will write this as, this is center, this is your mg. I am not taking this one. This is the periphery of the ring. Okay, this is center of the ring, and this distance I call this as d over here. Okay, if this is d, then this is your r here, because this is your full diameter of the ring over here, right? So this is your r, this is also your r. Now what is that you need? You need to find out mg into d into sine theta should now be equal to tau over here. Okay, this is gravitational force. Now what we do is, mg, what is mg here? Mg is nothing but a force, got it. D is a distance. And sine theta, what is sine theta over here? Sine theta is nothing but the theta angle between the force and the displacement vector. Everything is fine. But unfortunately, you see there is no d anywhere over here. So I need to express d in terms of r. So how do I do this? So what I will do is, I will write this as d, this distance is d, right? This distance is d, this is r, this is angle theta. So therefore, sorry, mg into d, I have not considered this one. Mg is like this, perpendicular distance is d, and I need to write down this one here. Okay, so now what I will do is, mg is known, d, this is your angle theta. So I know opposite by adjacent is nothing but your sine theta. d by r is equal to sine theta, or d is equal to r sine theta. So I will just write this as mg r sine theta. Now what is this? This is nothing but due to gravity. We have got it for gravity. Now what is that we need to know? So first part of it is done. Second part is remaining. How do I get the second part? Let me go to the next slide. The second part, once again, I'll draw this diagram. So okay, it's already here. So it is like this now over here. And this is my angle theta over here. Okay, this is my angle theta over here. And then the torque due to the magnetic. Okay, let me write down. The torque due to gravity is given by mg r sine theta. The torque due to gravity, sorry, torque due to magnetic force is given by the formula tau b is equal to magnetic moment multiplied by magnetic field multiplied by the sine of the angle between the theta and this one, the value of m. Okay, sine of the angle between them. Let me write this as alpha over here. Sine of the angle between the vector b and the vector m over here. M is also called as a magnetic moment vector. You will learn this, you would have learned this magnetic moment vector in one small line in atomic physics. Okay, there you would have said the magnetic moment of a what you call a electron, okay, if it is revolving around in a circular orbit, is given by current multiplied by area. Okay, so therefore current is not a vector, area is a vector. So it's an angle between the aerial vector and the magnetic vector. Okay, aerial vector, magnetic vector into sine alpha. It is definitely not equal to theta. I'll show you why is it so. Let us determine this. Now first let us write down the diagram once again. You know, physics has lots of diagrams. Without drawing diagram, don't attempt any physics. You will not enjoy this, and you will not get it correctly also. Draw correct appropriate diagram, only then you will get it correctly. So therefore now what we do is, this is my area, this is my circle, this is my loop, this is how it looks like this. This is my diameter of loop. So it looks like an ellipsoid, but there is no other way that I can draw it. So as a result of it, I am drawing like this. Now if this is my area, how do you draw the aerial vector? aerial vector would be perpendicular like this over here. This is your aerial vector. Always remember, aerial vector is perpendicular to it. You have already learnt the vectors. You know how do you write area? Area is equal to length into breadth, right? What is L? L is nothing but the length, and B is the breadth over here. So therefore, these two are nothing but your vectors over here. So it's a cross product of two vectors. When you have a cross product of two vectors, then this cross product will be perpendicular to the length and the breadth vector. So this is your aerial vector now. Okay, this is your aerial vector. So as a result of it, it's always perpendicular to the plane containing the length and breadth. Okay, that's how you have to consider over here. So for the circle also same thing applies. You will be able to prove it, but anyway I'm not proving here. That is not the scope of the the problem. So here the interest is only to use this. So therefore current is not a vector. So therefore I into A. What is A here? A is like this. What is B here? B is like this. B is like this, right? I mean, what is the angle between these two? This angle is alpha, but you know there is no alpha at all here. So what should I do? There is only one angle which is theta over here. Now where is that angle theta defined? The angle theta is defined like this over here. Okay, so this is your vertical, and this is my diameter. See, this is my diameter. This is my diameter here. The angle between the diameter and the vertical is theta. This angle is what is theta. If this angle is theta, then what you can get this one here is this alpha. This will be perpendicular here like this. Okay, so therefore, so you can see this value of alpha would be equal to 90 minus theta. The value of alpha would be equal to 90 minus theta. Okay, by geometry you can look into this. So if that is the case, let me substitute over here. This I will get this as A. What is A? Pi r square, area of the circle, which would be pi r square. B is called as B naught. B naught. And this one I will write this as sine of 90 minus theta, which once again I can write this as current I B naught pi r square cos theta. Now what did we say earlier? This tau B and tau G should be equal to each other, right? So let me go to the next slide. So if at a particular point, tau B should be equal to tau G, which should now be equal to, now let me copy these values. So I B naught pi r square cos theta, I B naught pi r square cos theta is equal to, what's the value of tau G? mgr sin theta. mgr sin theta. This r and this r cancels. What is that I need? I need tan theta here. Okay, so therefore, so I have pushed this theta that side. I get tan theta is equal to I B naught pi r divided by mg. I B naught pi r I B naught divided by mg, which is option A. Okay. So thus you observe that we already come to an end of how to solve these problems. Okay, so what do you need actually to solve these problems? You actually need to know that, and you need to know, okay, what are the math behind it. And if you know these two, then definitely solving an IIT problem should not be difficult. Okay, so with this I think we have come to an end to the second problem. Next problem, maybe after 2-3 days, would be able to look into that also. Okay, fine. Thank you very much. Do like, share, and subscribe to my channel for more such updates. So shortly, so we will be doing much more problems related to IB itself, IB and AS levels. So since there is vacation going on, so I thought why not we just focus on this and proceed with this. And this will also be useful. So for those, even if 1% of you decide to take up IIT exams, then this will be quite useful for you, and you learn a lot of concepts. Okay, that's how it has been useful. Okay, thank you once again for being with me.